Comparing shunt motor characteristics and series motor characteristics. The basics of DC machine is constant. Total power equals to TBIA, total power equals to torque into angular velocity. So from this, we are getting two basics. Back EMF is directly proportional to main field flux and speed, and torque is directly proportional to main field flux and armature current. This is similar for all type of machines. Either it may be DC generator of any type, either it may be DC motor of any type. So speed will be directly proportional to back EMF and inversely proportional to main field flux. Torque is directly proportional to main field flux and armature current. This is similar for both the machines, shunt motor and series motor. Now, as per the circuit diagram, shunt field winding is connected in parallel with the armature winding, and supply voltage is connected in parallel with the armature winding, similarly connected in parallel with the shunt field winding. So, shunt field current is supply voltage by resistance of shunt field winding. Resistance of shunt field winding is constant, so we can consider this as constant. So now shunt field current is directly proportional to supply voltage, and the relation between supply voltage and voltage drops is total supply voltage is equals to back EMF plus IARA drop plus brush voltage drop. So from this, back EMF voltage EB equals to supply voltage minus drop across armature and drop across brush. So we are ignoring this brush voltage drop and we are considering only armature resistance drop. And here total current is sum of the shunt field current and armature current. These two currents are taking two different paths. So shunt field current is directly proportional to supply voltage and armature current is directly proportional to load on the shaft. As this shunt field resistance is constant, terminal voltage is constant, so shunt field current we can consider it as constant. So flux is also almost constant. If terminal voltage varies, then only shunt field current varies, then only flux can vary. So here we are assuming that supply voltage is almost constant. So main field flux, that is almost constant. Now speed is directly proportional to back EMF. If load on shunt motor is increasing, that means armature current is also increasing. And from this relation, if armature current increases, IAR drop increases. As IARA drop increases, then back EMF will decrease. So as armature current increases, back EMF decreases, so speed will decrease. So instead of direct constant line, speed is slightly decreasing. This is when we are considering armature resistance drop. So drop across armature affects the back EMF. So if armature drop increases, back EMF decreases, and the relation between back EMF and speed is directly proportional. So if back EMF decreases, speed will decrease. For no load condition, the current is very minimal. This is no load current, but the machine is running at rated speed. This is NR, rated speed. From this position onwards, the load is continuously increasing. For increase in load, there will be slight decrease in speed. So under ideal condition, this should be the rated speed curve, but as load increases, the speed curve slightly decreases. But this can be considered as almost constant line. So torque is very simple. It is directly proportional to main field current and armature current. So main field flux almost constant. So torque is directly proportional to armature current. This is simply a linear curve. Torque versus armature current is simply a linear curve starting from origin. If we consider friction losses, and then torque on the shaft will be linear curve, but there is a slight shift of curve from origin. Whereas in case of series motor, series field winding is connected in series with armature winding. Load is on the shaft and this is supply voltage. In this circuit, total current is load current, that is also equals to series winding current, that is also equals to armature current. Here load is on shaft supply voltage, and this is complete circuit from series field winding, brushes, armature winding, and supply voltage. Load on the shaft defines the armature current. If there is no load, then the armature current is very low. If there is full load, armature current will be maximum. And there is no load means armature current is minimum. The armature current is equals to series field current. Series field current is directly proportional to flux. So if minimum current means minimum flux. So the relation between flux and speed is inversely proportional. Minimum flux means higher speed. So under no load condition, the armature current will be very low, so that speed will be very high. So here speed will be more than rated speed. As load increases, armature current increases. That means series field current is also increasing. As current increases, field increases. As field increasing means speed is decreasing. So this is armature current with reference to rated load, and this will be rated speed with reference to rated load. So initial condition, when the load is very less or the load is decreasing from its rated load condition, the speed will start increasing above rated speed. So this is above rated speed portion. So under no load condition, speed is very much greater than rated speed. When the machine is on rated load, then the speed will be rated load. As load decreases, speed will increase more than rated speed. So this is rectangular hyperbolic curve. So in this case, the speed is controlled by load current. The load current, which is also equals to series field current. So the main difference between shunt field motors speed curve and series field motor speed curve, why it is almost constant horizontal line and why it is rectangular hyperbolic curve. Because in case of shunt motor, the flux is almost constant, so speed is almost constant. In case of series motor, the flux is inversely proportional to speed. The flux mainly depends upon load current, as it is completely series circuit. So the load current, which is equals to series field current directly proportional to series field flux. If lower the series field current, then lower the flux, as the relation between speed and flux is inversely proportional. If lower the flux, there will be higher the speed. And torque curve is very simple. Torque is directly proportional to main field flux and armature current. So main field flux is directly proportional to series field current. Series field current, which is also equals to armature current. So under starting condition, torque is directly proportional to square of the armature current. So, and this is the position of saturation of series field pole. The pole which is carrying series field winding will get saturated. So this is the position where it may get saturated. Once the series field pole is saturated, and the flux generated by this machine will be constant. So afterwards, the torque will be directly proportional to only armature current, which is load current. So from here onwards, the curve will be almost linear. This is for torque in case of armature, and shaft torque will be simply considering frictional losses. So if we consider frictional losses, and there will be slight shift of curve on this x-axis. So in case of shunt motor, the flux was constant from the initial condition, whereas in case of series motor, the flux is not constant. Flux is variable. So because of that, in case of shunt motor, the torque is directly proportional to current from initial position. But in case of series motor, the flux is directly proportional to square of the current at the beginning till before saturation of series field pole. After saturation of series field pole, the torque will be directly proportional to current. So in case of shunt motor, speed means it is a horizontal line. In case of series motor, the speed curve means rectangular hyperbola. In case of shunt motor, torque means linear curve. In case of series motor, torque means parabolic curve before saturation and linear curve after saturation. These four curves are very important for series motor and for shunt motor.